Hello everyone and welcome to Kiru's online lectures. I am Kira Jamtani and today's topic is Aldehydes, Ketones and Carboxylic acids part 5. In part 1 we studied introduction, nomenclature and structure of carbonyl groups. In part 2 we studied preparation of aldehydes and ketones. In part 3 physical and chemical properties of aldehydes and ketones. In part 4 nomenclature, structure and preparation of carboxylic acids. Now in part 5 we are going to study physical and chemical properties of carboxylic acids. So moving on to the physical property of carboxylic acids. Aliphatic carboxylic acids up to 9 carbon atoms. They are colorless liquids at room temperature with unpleasant odors. Higher acids are wax-like solids. Lower carboxylic acids are miscible with water. Thus, we say solubility is inversely proportional to alkyl group size. Thus, as the size of alkyl group increases, solubility of carboxylic acid decreases. Monocarboxylic acids, like we have CH3COOH, this is monocarboxylic acids. So these monocarboxylic acids, they have higher boiling point as compared to aldehydes, ketones and even alcohols of comparable masses, and it is due to the reason that they have extensive association of carboxylic acid molecules through intermolecular hydrogen bonding. The hydrogen bonds are not broken completely even in the vapor phase. Like this is one carboxylic acid we have. So since there is intermolecular hydrogen bonding, this is the hydrogen bonding which is performed between two carboxylic acid groups. So this hydrogen bonding is not broken completely even in the vapor phase. In fact, monocarboxylic acids, this is the vapor phase. Monocarboxylic acid exists as, this is known as dimer, that this monocarboxylic acid exists as dimer in the vapor phase or in aprotic solvents. Now moving on to the chemical properties of carboxylic acids. So the first chemical property is reaction involving cleavage of OH bond. So when there is a cleavage of OH bond, it increases the acidity, it indicates acidity of phenols. So thus this carboxylic acid, it reacts with metals and alkalis. Now we have carboxylic acid, it reacts with metal, this hydrogen is liberated and thus we get RCOONA plus H2. Similarly, RCOOH, this bond will be broken. If it reacts with alkali, that is NaOH, it forms RCOONA plus H2O. Now RCOOH plus Na2CO3, it gives RCOONA plus H2O plus CO2. So these are the reactions which involves cleavage of OH bond. Now these carboxylic acids, they dissociate in water to give resonance stabilized carboxylate ion. Now like this we have carboxylic acid, it dissociates in water and it gives H3O plus ion and resonance stabilizing carboxylate ion. So this is resonance stabilizing carboxylate ion, where we can write equilibrium constant as H3O plus into RCOO minus by H2O into RCOOH. Now when this H2O is multiplied with equilibrium constant, it becomes Ka, which is acid dissociation constant. Thus the value of Ka comes out to be H3O plus into carboxylate ion by acid. Now, this for conveniency, basically the strength of acid is generally indicated by its pKa value, and we know this pKa is equals to minus log of Ka. So, HCl, its pKa is minus 7, whereas the pKa for trichloroacetic acid, benzoic acid and acetic acid, it is very small than as compared to HCl. So, smaller pKa, stronger is the acid. This HCl, it has a smaller pKa, thus stronger is the acid. So, we say carboxylic acids are weaker than mineral acids, but yes, they are stronger than alcohols and many simple phenols. Now, why? We can write over here HCl is more acidic than acetic acid, but acetic acid is more acidic than alcohol of comparable masses. But yes, this acetic acid is stronger than phenol also. It is due to carboxylate ion, which is more stabilized than phenoxide ion. So, therefore, we say the carboxylic acids are more acidic as compared to phenols. Now, moving on to the next concept, which is effect of substituent on the acidity of carboxylic acids. Now, we have carboxylic acid, like this is carboxylate ion. Now, if electron withdrawing group is attached over here, so this electron withdrawing group stabilizes carboxylate ion. It stabilizes carboxylate anion and thus strengthens the acid. But if electron donating group is present over here, so this electron donating group destabilizes carboxylate ion and thus weakens the acid. Now, the effect of the groups in increasing order is CF3 is more acidic, then NO2, then CN, then fluorine group, then chlorine, bromine, iodine and then phenyl group. So, thus if we want to calculate the acidity order, so we write over here CF3COOH is more acidic, then Cl3COOH, then CHCl2COOH and so on. So, this is acidity order of when substituents are attached in the carboxylic acid. Now, moving on to the reaction that involves cleavage of COH bond. So, the first is formation of anhydrides, carboxylic acid on heating with mineral acids. So, we have carboxylic acid like CH3, COOH. Now, when they are heated with mineral acids like H2SO4 or with P2O5, we get corresponding anhydrides. Thus, here occurs removal of H2O molecules. So, we get CH3, CH3CO, here O, C, O and CH3. We call it as ethanoic anhydride. Now, moving on to next, which is esterification. So, carboxylic acid are esterified with alcohols, or we can write phenols in presence of mineral acids like H2SO4 or HCl gas as a catalyst, and thus we get over here ester plus water. Next reaction that involves cleavage of COH bond, which is reaction with PCl5, PCl3, SOCl2. So, RCOOH, it reacts with PCl5, we will get RCOCl plus PCl3 plus HCl. But if it is PCl3, we get 3 moles of RCOCl plus H3PO3, and when carboxylic acid reacts with SOCl2, again this H and Cl will be removed. So here we get RCOCl plus SO2 plus HCl. Next reaction which involves cleavage of COH bond is reaction with ammonia. So we have RCOH plus NH3. Now here this H and OH is removed, thus we get RCONH2. So acids when reacts with ammonia, they form amides. Now the reaction that involves cleavage of COH bond, that is reduction. So here we have carboxylic acid, RCOH, they are reduced to primary alcohols by lithium aluminium hydride, or better reaction is observed when we take diborane over here, that is B2H6. So this diborane does not easily reduce functional groups such as ester, nitro, halo, etc. So sodium borohydrate does not reduce the carboxyl group. So therefore we take over here diborane, and then on acidification we get primary alcohol. Decarboxylation, that is carboxylic acid, they loses carbon dioxide. So when they loses carbon dioxide, thus we get over here CO2 is removed, we get RH plus CO2. Now over here the reagents which we take, that is NaOH and CaO in the ratio of 3:1. So this NaO combines with CO2 and we get over here Na2CO3. Now moving on to next reaction, which is substitution reaction in the hydrocarbon part. So first reaction is halogenation. Now in this reaction we have RCOOH. So over here basically what happens, it is RCH2COOH. RCH2COOH. So carboxylic acids which have alpha carbon, they are basically halogenated at the alpha position on treatment with chlorine, or we can say bromine, in presence of red phosphorus. So they react with halogens, any halogen it can be, in the presence of red phosphorus. Thus in alpha position this halogen is substituted and we get alpha halocarboxylic acid. Coming on to ring substitution. So we have over here benzoic acid. Aromatic carboxylic acids, they undergo electrophilic substitutions in which carboxylic acid act as a deactivating and meta directing. So thus we have two reactions over here. When we take bromine in with FeBr3, so this is known as bromination, and here in meta position this bromine gets attached, thus it is known as metabromobenzoic acid. Then nitration, that is concentrated HNO3 plus concentrated H2SO4. So over here we get COOH, and in meta position there will be attachment of nitro group. So it is known as meta-nitrobenzoic acid. So in today's video we studied about physical and chemical properties of carboxylic acids. Hope you guys are finding videos helpful. So do like, share and subscribe the channel. Thank you.